All right, so here's a problem. You can see the loads. It's hard to read, I know. That's half a kip at each point. This is a 2 kip foot moment. It's 40 feet long. And these are applied at 10 foot intervals. We want to find the shear moment at C. So you can imagine a cut here at C. The first question you want to ask yourself, since we're using method of sections, do you want to work the left side or the right side? Yeah, the right side I think is an easy one to see. If I did go left, I'd have to find all these reactions first. You can do that, but that's just more work. So let's work the left-hand side. Now, one thing we have to think about, let's draw the free body diagram for this. So I will. So there's that part of the structure at C. So what I'm going to do now is I'm going to assume a positive axial force at C, a positive shear at C. Now, why do I know that's positive? Because they take this part of the beam and rotate it clockwise. And then I'm going to assume a positive bending moment at C. And again, if you look at this beam, if I started to twist it, it would go up, and that would make that nice kind of smiley face that we talked about. Now out here on the free end, I do have a moment. And I've got here at E a half kip force. Here at D a half kip force, and I'll put the dimensions in. And now I've got this force at C. Now, do I include it on this body or not? Well, now it gets a little tricky. So I want to talk to you about, especially for point loads, being right underneath the point load gets a little kind of tricky. So we want to talk about being just to the left of the point load or just to the right. So let's think about just to the left to start. So if I'm actually making my cut, I'll under my free body diagram say to the left. So that means I'm really on the left side of C, just barely. So then my half kip force comes in, right? If I'm just on the right side, which would be like that, then see the half kip force is not there. If I cut it just to the left, the half kip force is there. What difference do you think that's going to make? Well, when I sum forces in the y direction for shear, in one case I will include it, in another case I won't. So that will make a difference in the shear. Will it make any difference in the moment? Well, that moment arm is basically 0, and it's not there. So it shouldn't make any difference in the moment. Let's find out. So starting, if this were the free body diagram, just to the left, I'll say left of C. So then we always like to start with summing moments. So I'm going to sum moments at the cut, and assuming right-hand rule for my sign convention, make sure this body's in equilibrium. So, what kind of moment is this using my static sign convention? It's negative. So I'll get minus the moment at C. The shear and the axial force don't create moment at C. This 1/2 kip does not, but these two do. And they create what kind of moment about C? Positive or negative? Negative. So I'll have negative 1/2 kip. The first moment arm is 10. The second moment arm is 20. And then I have the moment out here on the end. Is that positive or negative moment? That's also negative. So I should be able to solve for my moment at C. And when I do, I get negative 17 kip feet. Okay. How do you think this structure is going to bend under all these loads? Do you think point E is going to go up or down? Down. So it's probably going to bend something like that. What's that look like? Is that a half of a frown? I think it is. So that concave shape down like that, that's indicative of negative bending moment. So that's good. That seems reasonable. So let's go ahead and look at my shear forces by summing forces in the y direction. I'll assume up is positive. So my shear force is up, and then I have 1, 2, 3 forces down, right? Minus a half, minus a half, and minus a half. So it looks like my shear at C is equal to 1.5 kips. Yep.
Can you explain why your shear pointed up?
That's positive shear. So remember, positive shear will take the section and try to rotate it clockwise. Think of this like a hand on a clock. So this end here, is it going to go up or down with the shear force? It's got to go up, right? So that's rotating clockwise. So positive shear always rotates the end clockwise.
Would it be incorrect if we had cut to the right?
We're going to do that next. You're seeing the future, Mr. Riley. I'll just incorrect's not the right word. It would be it's a different problem kind of. So let's go ahead and I'll clean this up by just saying I'll sum forces in the x direction. All I have is the axial force. In this case, it's 0. So let's do that. Let's see what happens when I draw the same free body diagram, except I'm going to go to the right of C. So what changes? Well, the geometry is unchanged. I still have my load out here of 2 kips per foot. I have the load at E, half kip. I have the load at D, half a kip. But I'm to the right of C now, so I don't have the load at C. Before, when I cut to the left, I could see the load. When I cut to the right, I don't see it. And since these cuts are very, 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 very small, very, very close, the dimensions are the same. I still will assume positive shear. I should put little positives here to indicate that I'm doing the positive sign conventions. There's my axial force at C, positive, and then there's my bending moment. And I just do the same problems. I just redo the problem. So again, right-hand rule for my sign convention, summing the moments at the cut. What do I get? Well, this is still, with my sign convention, that's a negative moment. These two forces also create negative moment. The force is half a kip. The first one is at a moment arm of 10. The second is at a moment arm of 20. Now here on the end, I have a negative moment of 2. So when I solve for the moment at C, I get minus 17. So there is no change in the moment as I go from the left side of an applied force to the right side. So this applied force is not causing the moment to change instantly. What about the shear? Well, we have to do that, compute that by summing forces in the y direction. So let's see what I got. I got shears acting up, 1, 2 forces acting down, 1/2 shear, 1/2 kip, 1/2 kip. So you can see compared to the first time, the shear has changed. It's only 1 kip. So if I made a quick little plot, see if I have room down here to squeeze this in. So if I plotted the moment, and I did it right here at point C. Oh, they're going to come out negative. I'm going to mess this up. I'm going to write that I'm doing the negative moment. So it's going to come in. I don't know what the shape's going to be, and I'm not too worried about that right now. But it's going to come in at some value, and at C, is it going to change? No. It may go out at a different slope, but the value is still the same, unchanged, as I went from the left side to the right side. Okay? What happens for shear? Let's see if I can squeeze this in right here. So now if I'm looking at shear, and again I look at a value, I want to make sure you can see it, C, what's going to come in on the left side at 1.5, whatever the shape is, and it's going to go out at 1. So there's going to be a dramatic change in shear, an instantaneous change in shear. And what is that going to be exactly equal to? The value of the applied load, P. So we can use that to our advantage. So that means every time we go from the left side to the right side, which is basic Cartesian coordinates, moving from left to right, my shear is going to drop. Every time I hit one of these applied forces, it's going to drop. Now, of course, if the force is up, what would happen? The shear would step up. So there's really not a value for shear at an applied force. It's a lot of values. So you're really looking at what's the shear on one side and then the shear on the other side. And all we really care about usually in design is the maximum value. So we'll do more of that, but I just want to kind of show you where we're starting off. Okay.